All right, this video is going to be about volumes of solids, but this time not solids of revolution, solids using cross sections. This will be a different kind of solid than the solids that we've seen so far. In fact, let's review what we know so far about volumes of solids. So far, we've been working just with solids of revolution. So what we've done is we have some sort of a shape. Maybe it's like this in the 2D area. And then we revolve that around an axis. Simple case like this, we put a rectangle. In the case of a disk method, we put that rectangle perpendicular to the axis of rotation. When we rotate the solid around, we get this 3D shape like that. When we rotate the disk around, we get a disk shape, right, that like this. And then that disk has a little a height here, which is a little change, let's say in the height, and then it has a radius. And then the way we find the volume is we sum up the volumes of cylinders, right, which is pi r squared, and then that little change in height in whichever direction it is, from some starting to ending value to cover all the rectangle areas in the original 2D area. For shell method, we do something similar, right? For shell, we have a rotational solid. Let's say we have something that looks like this, and we're also rotating it around the y-axis. So we get the other shape over here that looks like this, right? So we have a rotational shape like that, kind of, right? And then we add a rectangle, but this time growing from an x or y axis that's parallel to the axis of rotation. And then when we rotate that around, it forms a shape which is called a cylindrical shell, right? So you have a shell shape like that, and that has more dimensions. It has a radius, and then it also has a height, and then it also has a little change, but this time the change is in the radius direction. So the volume is summations of 2 pi r h dr. And there's whole cases too where we have to subtract off another shape inside that one or something like that. But the basic idea here is that so far all of our volumes have been rotationally symmetrical because they've been formed by rotating some particular shape around an axis. And then we also have a volume that we're summing based on a rectangle that's been rotated as well, either a cylinder or a shell shape. But these are still volumes. This is just volume of a disk, and that, including the H, this is volume of a shell. So what we're going to do now is branch out and take volumes, which are summations of other sorts of volumes that are not disks and shells, and that allows us to find volumes of a wider variety of shapes. So let's say, for example, that I wanted to find the volume of a pyramid. Okay, so let me kind of draw that here in 3 dimensions. If we had a pyramid that looked like this, let's say, okay, then you could imagine taking a slice out of that pyramid. If I just go partway through and just took a slice, that slice would have a cross-sectional area. And that cross-sectional area, in this case, maybe it would be a square if this was a square-based pyramid. There would be a little thickness to the object like this. I'm going to exaggerate it here. And so we'll still have some sort of a thing that we integrate over, right? But I'm going to try to do everything still in terms of a single variable. So imagine that you formed this volume of this solid by summing a whole lot of squares. There's one selected square, but there would also be a square up here, a square down here, and all of these little squares would be summed up. As long as I can find a way to figure out the area of that one cross section, which I'll call the cross-sectional area, then I can use an integral to sum up those cross-sectional areas times this little width here, and that will give me the volume of the solid. So what we'll be doing is sketching a 3-dimensional solid, right, and then also a 2-dimensional picture of the cross-sectional area. We'll figure out what variable we're summing along, and we have to write everything in terms of that variable. That variable we sum along will be perpendicular direction to where the cross-section area is expressed. We're going to have to determine a formula for this cross-sectional area, but this time it'll be on a case-by-case basis. So we won't be using pi r squared dh or 2 pi r h dr, because those are standardized forms. Now we'll use some other area, okay, that we figure out that matches the problem. And then we'll sum those cross-sectional areas with an integral to find the volume. So best to see this with just some examples. Let's start with this one. It says, find the volume of the solid formed by the cross-sections which are perpendicular to the x-axis and they form squares. The base of the shape is in the xy plane defined by the curves y equals x squared, y equals 0, and x is 2. All right, so what I would do for this kind of problem is first draw the two-dimensional base. Okay, so that's in the xy plane. And it says that we have the curve y equals x squared, y equals 0, and x is 2. Okay, and if I put 2 squared in there, that would go up to 4. And so that definitely forms a two-dimensional region here. Okay, what they're saying is this is the base of the shape. And then we're going to have squares which are perpendicular to the x-axis that form the solid. So to graph the solid in 3D, I'm going to switch to graphing in 3D. Now, the way I graph in 3D is I make it so that this third axis, which I'm going to call z, is up, and then y is to the right. And then x has to be perpendicular to both of those, so technically it has to come straight out of the screen at you, but I can't really draw that on a 2D surface, so I'll draw it down and to the right, representing that it's coming out. But we understand that these are all perpendicular to each other. Okay, so now I'm going to just recreate my 2D sketch, but down here on the xy plane. So this is the y equals x curve coming up like this, right? And then here is the line x is 2, that's 2. And this comes up until we get to 4 out here, like that. The area that I have shaded there is this, okay? And so I have, that's the base of my shape. Okay, so now we're going to try to draw in one of these little cross-sectional areas. They say it's perpendicular to the x-axis, right? And it's gonna be contained by this base. So I'm just going to go partway through here and just draw a line that's perpendicular to the x-axis like that, okay? That is the base of the shape. And it says the cross-section is a square. So that means that I would build this up into a square like this, okay? And that's just one of these little squares. Now I'm going to switch to a different color and draw the other squares in. Let me switch to a lighter color, like let's try this color, okay? And I'll draw some more of the squares in here, right? So there's also going to be a square out here, right, that looks like this, maybe. And there's going to be a square back here that looks like this. And all of those squares together, if I sum them all the way over the space, that's going to form a three-dimensional solid, okay? There'll be a square out here too. All right, so let me go back and highlight that one that I've selected in the middle. Okay, this is a little square, okay? Now, that's going to have to be turned into a volume. So we're going to have to imagine that I'm giving it a little infinitely thin thickness here. I'm exaggerating it. And because the shapes are perpendicular to the x-axis, this is going to be the direction that we're integrating over, which is the x. So that means this little width here is dx. So the volume of that cross-sectional area is just going to be equal to the area of that square times dx, right? So if I find this area of this square and multiply by dx, I get the volume of a little box. All right, so now to do that, I'm going to put another label on here. Let me switch colors again. Let's go to purple. And I'm going to label the bottom of this B. That length right there we're going to call B. And that means that the area of this square, which I'll now shade in, that area is B squared, okay? Now I'll switch back to my 2D picture and also draw that little B. That B is perpendicular to the x-axis, so it's here. Okay, that's B. And I have to somehow find an expression for B so I can plug it in for my area expression, but it has to eventually use only x's, right? So this B is a y direction, but what sets this B is this curve here, which is the curve y equals x squared. And so that means if I solve this this y in terms of x's, it's already solved for that. It's just x squared. So this b is x squared. That means this distance down here is x squared. So if I take x squared and then I square it, I'm going to get the area of that little shape, When I multiply it by dx, I get a little volume. And then finally, we can go ahead and form the volume. The volume is going to be a sum of those areas of squares, the cross-sectional area times dx. So in this case, that is x squared squared. And then finally, to finish this, we'll just sum x's. And that means we're going to sum a lot of different b's here, starting at x equals 0 and ending when x gets to 2. So 0 to 2. That would be the setup, and all we're doing on the test is setups. If we were to do Math 9, which I won't use video time to show you, we would get a numerical area, but it represents the volume that's enclosed by this weird shape here, okay? Kind of a cone shape that's irregular. All right, so that's how we do volumes of cross-sectional areas. If you want to think of it as a procedure, first, I think you should sketch the 2D region, the base region. And then second, start trying to figure out in 3D what's going on. That usually means that then you have to put third the shape on to this, and then identify where the base is and put that same base back on the 2D picture. Figure out next what direction you're integrating in, so you know what variable you have to have everything in terms of, and then go back and figure out what the base is in terms of that variable, and then finally form the volume by taking the cross-sectional area times the little differential width and then summing across that integral. All right, let's look at a few other examples here. Let's say that the base is bounded by y equals x to the 1/2, which is the square root of x, and then the line x is 9, and the x-axis. Sections are perpendicular to the x-axis, and they're semicircles. Find the volume. Okay, so this one I've already got kind of sketched out. We have a 2D drawing here that has the square root of x curve written, and then I copied that over here. So here is an x, y, z three-dimensional sketch, which with that same section shaded in here from x equals 0 to x is 9. And then I've drawn in the cross sections. They said they're perpendicular to the x-axis here, right? But they're semicircles like this, and that forms kind of this weird deformed half of a football shape. Find the volume. Okay, the next thing I would figure out, now that I've kind of got a handle on that, is what is going to be the integration variable. And so since we're perpendicular to this is in this direction, we're summing in this direction, that's x, which means we're going to end up with a dx, a little change for the thickness. The next thing I would do is go back and try to figure out, okay, what is the base? So let me highlight that with a different color. I'll use orange. So the base of one of these is this right here, right? That's the base. And so, or here's one here. There's that base right there. We have to figure out a way to express that base using an x variable. What's setting that is the y, which is the square root of x. So that means the base is the square root of x at any particular x. And then we have to come up with an area of the cross section. So since this is half of a circle, pi r squared is the area of a circle. If I take half of it, it's half of pi r squared. And then the radius, let me change colors again. The radius here is actually only going to be this much. So that radius is only half of a base. So if this base is the square root of 2, let's start working over here on the cross-sectional area. I'll write it over again. We know it's going to be 1/2 pi r squared, but we also know that the radius is half of a base, and we know that the base is the square root of x. So I have to put 1/2 times the square root of x in for this r. And I would get 1/2 and then pi, and then the radius, which is 1/2 of the square root of x squared. That gives me the area of the cross section. And it looks like we've got that simplified down here to just pi over 8 times x. And so then you just take that area here and you plug it in. Now, because we're saying that you don't have to simplify, you're welcome to leave this like this. This is the area of the cross section. And then just multiply it by that little thickness and integrate it from some starting to ending x value. In this case, it's from 0 to 9. And then that would be the answer on the test. Okay. So the one thing that'll be true about all these is that they're perpendicular to the axis where we're integrating along. Okay, let's look at a couple other examples. So the base of the shape is a circular disc with radius 9. Parallel cross sections are perpendicular to the base and they are squares. Okay, so let's draw the 2D shape. It says in the XY plane that we have a circle of radius 9. Actually, yeah, let's change that to 3. I'm going to change this to 3 just to make it easy. No, we could leave it 9. Doesn't matter. Let's leave it 9. Okay, so we have a circle of radius 9, and that is the base of the shape. Okay, so let me try to draw 3 dimensions to picture this. So now Z is up, Y is over here, and X is here. If I try to draw that same shape, it'll be a circle on its side, something like this. Okay, and then inside there, I'm going to cover that in cross sections, which are squares. It just says perpendicular to the base, so I could draw them either direction. Just for consistency, let me stick with X as the integration variable, so that our volume is going to be some integration with respect to X. If that's true, then I need to put my base in perpendicular to this. So I'll just go out here and draw a base. And then one of these shapes is going to be a square like that. And so what will happen is the other shapes, if I were to fill the rest of them in, I'll try to do them behind here using a lighter color. There's going to be all these other squares, like there'll be some squares that are like that, right? And then back here, there'll be more squares. There's a whole bunch of squares here forming a shape like that. So it's forming kind of this weird kind of half, well, it'd be half of a not quite half of a sphere, right? Because it's got a cross-sectional shape. It's like a square that is forming a kind of curve like this. All right, so let me go back and highlight that one cross-section in the middle with the red. Okay, so there, let's figure out where the base of that is. And again, I'll use another color. Let's use purple for that. Okay, so this right here is the base. That's B. And if I were to draw it here, it would be there. That's B. Okay. And my goal is I have to come up with some way to find the cross-sectional area here. So that cross-sectional area is going to be the area of a square, which whatever B is just going to be squared. But I have to write that B in terms of X. So right now, this B, well, it's established by both sides by this curve. So let's take this curve. We're going to have to first make an equation for that circle. So hopefully you know that centered at the origin, the circle would be x squared plus y squared is radius squared. And then since this B is in the y direction, I'm going to solve this for y. So y squared equals 81 minus x squared. And so y would be plus or minus the square root of 81 minus x squared. All right, perfect. Now, there's a plus and a minus here. So this top number here, this one would be the plus square root of 81 minus x squared. And on the bottom here, we would have the negative one, 81 minus x squared. So B, let me switch colors back to the B color here. The B is going to be the difference between those two, top minus bottom. So B would be square root of 81 minus x squared minus, and then negative square root of 81 minus x squared, which this is just going to add. So the B would be 2 square roots of 81 minus x squared. And that means I've got my base written in terms of x. So therefore, over here at the cross section, that base squared would be 2 square root of 81 minus x squared, and then squared, which means the 2 squared would be a 4, and this squared would cancel out the square root and get 81 minus x squared. So that's what I've got to put in here for my area. I've got 4 81 minus x squared. That's the area. And then when I multiply that by that little thickness in the x direction, I get a volume. And then finally, I have to sum that volume over a range of x's. So let's go back to the 2D picture again. right? If this is radius 9, then that means we're going from over here at x is -9 all the way over here to +9. So we have to integrate this from -9 to +9, and this would be the answer that you could use on the test. In fact, you could even plug this in as is for this. You wouldn't even have to do this simplification. Okay. Okay, those few examples should hopefully get you enough to get started so you can try the homework problems, give those problems a try, and then ask your teacher for help in class when we go over this topic. Thanks for tuning in.